Good afternoon. Today, in light of my having graded the homework, we're again going to go over the homework problems from the last problem set. I've already said something about some of these in class, but we're going to look at them a little more closely. I'll begin with problem A-29, which treats a ramp and a mass. The objective of treating the mass and the ramp is that the ramp does not sit still. It has a sideways acceleration a due to the rocket motor that's plugged into it. The mass sits on the ramp. The mass actually does not move with respect to the ramp. The mass, however, is attached to the top of the ramp by a spring, so there are a number of rather different forces acting on the mass. And we are asked how much the spring stretches if we're at the equilibrium position. So here we are, about to start the problem. The first thing we do is to draw a sketch of the problem. The sketch of the problem shows roughly what the problem looks like. So if you look at the sketch, we have a mass, we have a spring attached to the mass, we have a ramp, and the ramp is accelerating sideways. The sketch of the problem simply fixes our mind on what is going on. The sketch of the problem is not actually a piece of the solution. For the piece of the solution, we need to draw the force diagram. The force diagram is here. The force diagram shows all of the forces acting on the mass of interest. As a result, there's the normal force perpendicular to the ramp surface. There's the force of gravity pointing straight down, and there's the force due to the spring. The spring is mounted parallel to the ramp, so it delivers a force of magnitude length of the spring minus its equilibrium length. Notice that that force is a magnitude. Should there be a plus sign here or a minus sign? Well, it depends. Which way is the spring force pointing with respect to the coordinates? If you don't like the sign that you have in front of you, you can always flip the coordinates around until the sign is correct. Having said that, we get to choose coordinates. Indeed, in order for this little picture to be a correct picture of the system, you absolutely positively have to choose a coordinate axis, or you don't have a correct force diagram. There are two reasonable choices of coordinate axes. I've indicated one of them here. The x-axis is parallel to the table surface in the direction of acceleration. The y-axis is perpendicular to the table surface in the direction of acceleration. Your other choice would be to say the x-axis is parallel to the ramp, and the y-axis is perpendicular to the ramp. Remember, it doesn't matter what coordinates you use to solve the problem. Any marginally sane set of coordinates will indeed lead to a solution. However, some choices of coordinates are less painful than other choices of coordinates, and I'm trying to emphasize choosing less painful coordinates. So what's the best choice of coordinate? The x-axis could have the acceleration lying along it. There's the acceleration. And if I use these coordinates, the acceleration is all in the x direction and not at all in the y direction. I could also say that I'll choose coordinates in which the x and y axis are parallel and perpendicular to the slope of the ramp. If I choose the two coordinates, though, to be parallel and perpendicular to the ramp, I should remember that now there's a non-zero acceleration parallel to the ramp, and there's a non-zero acceleration perpendicular to the ramp, and the components of those two accelerations have to be determined by trig. Well, we've talked about determining components of forces using trigonometry before, and most of you actually have that one nailed down quite nicely. What we would be doing instead in this particular case, the case we're not following, is to break up the acceleration into components. Okay, we're going to use the coordinates you have indicated right above the arrow in the figure, and because we're using those coordinates, the acceleration will be all in the x direction and not at all in the y direction. Now let's push ahead, and in order to write the second law, we have to break the components into pieces. So let's break them into pieces. As always, our ramp makes an angle theta with respect to the horizontal, and I have drawn the theta into the figure. Because I've drawn the theta into the figure, I get to break the normal force and the spring force into components. Gravity is very easy. It points straight down, parallel to the y-axis, and because it points straight down, because it points straight down, it only has a non-zero y component. So here is the spring force whose magnitude is k times the change in the length of the spring. We'll choose things so that a positive delta L leads to the spring becoming longer, that's what's going to happen, and pulls the mass uphill. In that case, the force is in the indicated direction. There is a right triangle here. The two legs of the triangle, the horizontal leg and the vertical leg, are parallel to the coordinate axes. The full force is always the hypotenuse. And now, since the angle theta is right here, we can break the force into its components. And there's a component k delta L cosine theta parallel to the x-axis, and a component k delta L sine theta because this is the opposite to the angle theta, parallel to the y-axis. Having said that, I now have to put in pluses and minuses. Remember, the pluses and minuses are determined by the way you inserted the coordinate axes. If you inserted the coordinate axes reversed, say, 180 degrees from what I did, all of these signs would be about to flip. But we didn't. We choose my coordinate axes up here, and therefore the spring force has an x component in the minus x direction. That's where the minus came from. And the spring force has a component in the plus y direction. That's where the plus came from. Now let's come over here and look at the components of the normal force. Again, theta is the angle between the ramp and the x-axis. We'd like to know, here's our normal force. We'd like to break it into its x and its y components. And in order to do that, we need a little trig, and we need to know an interior angle of this triangle. Down here is theta. All right, the x-axis is horizontal. The bottom of this right triangle is also horizontal, so the two lines I just described are parallel. The ramp surface is a straight line cutting two parallel lines, so this angle is theta, and therefore the angle here must also be theta. If the angle that I've just marked is also theta, it must be the case G. The normal force is perpendicular to the ramp, so there's a right triangle here, and therefore this angle marked by the double arc must be the complement of theta. If that interior angle is the complement of theta, theta is up here. So this angle is theta. The leg of the right triangle adjacent to theta is n cosine theta. The leg of the triangle, it's a right triangle after all, opposite to theta is n sine theta. What about sines, plus and minus? The first component points to the right. The second component points up. Those are in the plus x and plus y direction. And so we have a plus sign here and a plus sign there. We have now written the force diagrams and are ready to advance to the second law. The second law itself is force equals mass times acceleration. Because this is the grown-up course, I have written the force F as a vector, and I have written the acceleration as a second derivative. When I actually break this up into components, I will sort out the y acceleration. There's the y acceleration, and there's the x acceleration. The thing to remember is that a vector equation is just a symbol for three scalar equations. So I started here and I have a vector equation, and I have now broken the vector equation into 1, 2, oh, you can't see it, can you? But 3 scalar equations. There's a scalar equation for the y components, there's a scalar component equation for the x components, and there is a scalar equation which you can't see because there's nothing in it, a scalar equation for perpendicular to your screen. That's the z equation. Well, I didn't bother to write the z equation down because nothing is happening in the z direction. Okay, in the y direction, and I've made a little parenthetical note here, the y acceleration is 0 and the right side of this equation is 0. In the x direction, well, the acceleration is all along the x-axis, so this m d square x dt square term is m times little a, where little a is the constant representing the actual acceleration. On the other side of the equation, I plug in for all of the components. And so the y component of n is n cosine theta. There's the n cosine theta. The y component of the spring force is k delta L sine theta with a plus sign. There's k delta L sine theta with a plus sign. And the gravitational force, which points straight down, here it is pointing straight down. Because I chose y to be upwards, the gravitational force is minus mg. In the x direction, I pick up the x component of the normal force, that's n sine theta, and I pick up the x component of the spring force, that's minus k delta L cosine theta. I have now written down the second law. The two equations that you see for the second law are sometimes called equations of motion. They are called equations of motion because they are the equations whose solution describes the motion of the system. You could have decided to use the other coordinate axes. In that case, n would have only had a y component. The spring force would only have had an x component because they're parallel to y and x. And the force of gravity would have had both x and y components. However, if you choose the coordinate axes to be these axes, y and x, you're okay. But if you instead chose y perpendicular to the normal surface, and x parallel to the surface of the plane, you would discover that over here you had both a y and an x acceleration, and you would have had to break the acceleration vector into its components. We have avoided doing this. We now advance to problem A-28. We have a right triangular block sitting on a frictionless table. Resting on the hypotenuse of the block, you have a picture, we'll see it in a moment, is a mass m. The hypotenuse makes an angle theta with respect to the horizontal. We've also attached a rocket motor to the back vertical side of the block. The rocket motor is fired, bringing the block to a constant acceleration, d square x dt square equals a. The mass m is then released so it is free to slide up or down the block. If the rocket's thrust is properly chosen, and the block is only released after the rocket has cut on, there is a value of a such that the mass just sits there. It doesn't slide up the block or down the block. You are being asked to calculate what value of a is needed. Notice that in this problem, I've specified the coordinate, at least in the sense I've said it's the horizontal acceleration that's a. Here is our solution to problem A-28. We begin with a sketch of the problem. There's the rocket motor. There is the block. There is the angle theta. There is the mass little m. The sketch of the problem is not a force diagram. It would still not be a force diagram if you wrote forces on the picture so that you had a force N headed off this way, and you had a force minus mg headed off straight down. A force diagram is a somewhat stylized picture, and there are rules for drawing one. In the correct force diagram, the mass is represented by a point. Each force is represented by an arrow coming from that point. The forces that are shown in a force diagram are the forces acting on the one mass, not forces acting on some other mass. Thus, the thrust TH of the rocket engine, there's the rocket engine, the thrust TH of the rocket engine acts on the right triangular block. It does not act on the mass little m, and should not be shown as acting on the mass little m. Finally, we choose our coordinates. The reasonable choice of coordinates is to have x horizontal and z vertical, in which case the acceleration is all on the x-axis. Furthermore, in those coordinates, the force of gravity is all on the z-axis. The normal force, though, points off in the indicated direction, and because the normal force points off in the indicated direction, it has components in both the x and z direction. How do we find those components? Here's the angle theta again. Up here is another horizontal, and since the horizontals are parallel, the two included angles theta and theta must be the same. The angle here inside the right triangle that's going to be used to decompose n, that angle is pi over 2 minus theta. It's the complement of theta, and the angle theta is found up at the top of the corner of the triangle. Now, to decompose n into its components, we draw n as being part of a right triangle. The force being decomposed is the hypotenuse of the right triangle. The force components are the x and y and the z components, and they are the two legs of the right triangle, in this case n sub x and n sub z. This is the angle theta, so the side down here is the opposite of theta. It's n sine theta, that's n sub x. And similarly, this is the side of the triangle adjacent to theta. It is n cosine theta. We now advance to writing the equations of motion for the system. We start off by actually writing correctly the second law. Force is mass times acceleration. Acceleration is a second derivative as shown. We then break the force into components. Once we've broken the force and the second law into components, there are as many equations as there are components, because the vector equation is just a symbol for its component equations. In addition, there's only one equation for each component. The second law you observe is force equals mass times acceleration. If you just wrote force equals bunch of terms, you might have written something that's actually true, but summation of the forces and a list of the forces is not the second law. The second law is that the force in the x direction, there's only one, n sub x, gives me mass times the acceleration in the x direction, and the sum of the forces in the z direction, that's n sub z and minus mg, gives me mass times the acceleration in the z direction. However, our mass remains stationary. Because it remains stationary, its vertical acceleration must be 0, and therefore n minus mg is 0. That's a nice equation. And the acceleration is, from this equation, n sub x over m. Okay, we now have the components of the acceleration. And if n sub z is equal to mg, then the hypotenuse of the triangle, here's the hypotenuse of the triangle of which n sub z is a side, must be mg over cosine theta. We also have, though, that n sub x is mass times a, the a being supplied by the rocket engine. How large is n sub x? Well, n sub x is n sine theta. So here is n. It's mg over cosine theta. Here is the fact that we only want the sine component of that, and that's equal to ma. However, I divide through the a, so a is equal to nx over m, and I have a equals n sub x. There's the m, and therefore a is equal to g sine theta over cosine theta. There's the problem. If we increase the acceleration, then n sub x and n sub z have to increase. We would then find n sub z is larger than it was before a was increased. And that has a consequence. And the consequence is that n sub z minus mg would be positive, and the block would accelerate up the ramp. Let us now proceed to problem 27. The figure shows two masses m1 and m2 suspended from strings. The strings go over a pair of pulleys and connect to opposite ends of a nearly massless spring. The spring has spring constant k and unstretched length L. By how much is the spring stretched from its equilibrium length? That's a fairly straightforward problem. How do we attack it? The first thing we do is to draw a sketch of the system. So here is the sketch. There is the mass m1, there is the mass m2, there are the two pulleys, and our target is defined by how much the spring has been stretched. So our first step is to draw the force diagrams for the objects in the system. So on the mass m1, there is a force of gravity m1 down and a tension force up. On the mass m2, there's a force of gravity m2g down and a tension force T up. The tension forces propagate along the strings. They propagate along the strings, so this mass is applying a tension force T at one end of the spring, and this mass is applying a force T on the other end of the spring. I've implicitly included something that is not quite obvious. The spring is massless. Therefore, the tension forces T on the two ends of the spring must be equal to each other, and when we get back from the spring down to the two masses, the tension forces are both equal to each other still. They're both still T. These are a complete set of force diagrams because I've included the coordinates. Now, there are a few things that may not be quite obvious here. The first thing that may not be quite obvious is that these are the forces on m1 and m2. The spring force acts on the string. It does not act on m1. It does not act on m2. And therefore, there is no force K delta L on either mass. Let us advance from the force diagrams to the equations of motion. We begin with the second law, force equals mass times acceleration. Force is a vector. It's represented by the letter F. The acceleration is a vector. It's represented by the second derivative, d squared r dt squared. We now go and write the equations of motion for the two masses. We could also write it for the spring, and we would have t minus t equals 0 times the acceleration of the spring. That's not very interesting. So on one mass, the forces are t minus m1g. On the other mass, the forces are t minus m2g. And these are equal to the mass times the two accelerations. Notice that when we go from the vector equation to the scalar equation, all of the vector symbols go away. The vector symbols go away when you write component equations because component equations are scalar equations that do not show vectors. At this point in the problem, a certain number of people went wildly wrong by writing t equals mg. There's no basis for that claim. That would only be true if the accelerations were 0. Well, a couple of people did write that the accelerations were 0, but you know, there's no basis for that statement either. The strings go over pulleys and are therefore free to move. Several people tried calculating the force diagram and forces on the strings. And this gives you a horizontal force due to the G. It's the spring. We have a vertical force due to the contact with the mass, and that is a force, the force T. We also have a force due to the pulley, which points sort of at a 45-degree angle. And you have the minor issue that you have no idea what the size of the pulley force is, so writing the equation of motion for the string doesn't seem to have done anyone, or almost anyone, any good in getting towards a solution. We do, however, have a constraint. And the constraint is that the vertical accelerations of the two masses have to be equal in magnitude and opposite direction. Notice that those are the accelerations which are constrained, not mass times acceleration, the forces. The forces on the two masses do not have to be equal. So for the first mass, we have t minus m1g is minus m1 d squared z1 dt squared. And I have replaced z1 with z2 using this equation. I now take this equation and subtract it from this one. Subtraction is the extremely rapid and effective way of eliminating t. And if I do the subtraction, the two t's cancel. I get the difference between minus m2g and minus m1g. Here is the difference. And that is equal to, well, we subtracted, so we have an m2 times the acceleration and minus a minus m1 times the acceleration. We have m1 plus m2. We divide m1 plus m2 to the other side, and we have an acceleration equation. So there is the value of d squared z2 dt squared. We'd also like to know the tension. To find the tension, we have to do something. We have to reach into our equation for the tension and replace the vertical acceleration that we just computed with its value. Here's the value of the acceleration times m2 in terms of known constants. If you just wrote this for the acceleration, or took the m2g to the other side and had t equals m2 d squared z2 dt squared minus m2g, if you wrote that, you wouldn't have solved it all, you wouldn't have a solution, and your answer would be incorrect. Finally, from the interaction between the spring and the string attached to it, we know that k delta L is equal to the tension. This is a point at which people sometimes become confused. K delta L is the force that the spring develops at each end. So the force that the spring develops at its left end matches the force on the spring at the left end, and that the force that the spring develops at the right end matches the force on the spring at the right end. And by the way, since the spring is massless, those two outside forces on the spring have to sum to 0. So we come back and we have that the tension is equal to K delta L. Notice that K delta L is applied at each end of the spring separately. It doesn't get divided between the two ends. K delta L is the force at either end of the spring. And if I plug K delta L equals T into our equation for T, I find, once I divide K to the other side, the value of the change in the length of the spring. We finally reach A26. A26 is our last problem. We have a mass on a ramp. The ramp can move to left or right. It's frictionless. There's a spring constant K spring with unstretched length L attached to the ramp at its top, and the mass M at the bottom. And we ask, by how much is the spring stretched if the mass M and the ramp are both stationary? This is just a special case of problem A-29, which we have already worked. The one difference is that the acceleration is 0 here and was A in problem 29. Let's go ahead and look quickly at the solutions. So here we are at problem 26. The first thing we do when we have a problem is to do a reasonable sketch that shows all of the quantities that will appear in the problem. So there's the angle theta, there's the mass m, there is the spring constant K, and there is the right triangular block on which the mass m is resting. That sketch is not a force diagram. The first step after we have the sketch is the force diagram, and in a legitimate force diagram, each mass is represented as a point. If you are representing the mass instead as a little sketch of the mass, your force diagrams are wrong. Coming out from the little point are a series of arrows, one arrow for each force. If there are several arrows pointing in the same direction, that doesn't happen to be the case here, the reasonable thing to do is to show each arrow coming out of the point and slightly displaced left or right. However, to complete our force diagram, we also need to have a set of coordinates. And so here I've chosen a set of coordinates. We didn't have to choose the coordinates x and y to be parallel and perpendicular to the ramp. Indeed, in problem 29, we did exactly the opposite. We chose x to be horizontal and y to be vertical. However, these are a perfectly legitimate set of coordinates. Remember, if you can solve the problem, you can solve the problem in whichever coordinate system you prefer. You don't have to use the coordinate system that seems obvious. There is, however, a general rule of thumb on choosing coordinates that may often make life less painful. If you can reasonably choose one of the coordinate axes to lie along the direction of acceleration, then along the other two coordinate axes the acceleration is 0, so we have equations for the force equal ma, but a is a 0 and the equation simplifies. Okay, that's the coordinate system, and now we proceed to the second law. You see here the second law. The second law is F equals mass times acceleration. F is the total force on the mass of interest due to the outside world. F does not include any forces on other objects. F does not include the mythical force of acceleration, or, I saw this in a series of homework problems, the force of velocity. F just includes the forces on the mass of interest. Some of you, for some reason, have taken to writing instead of F, sigma times F. The answer here is that in good physics, for the most part, we represent physical quantities as single symbols. If we need to tell them apart, we use subscripts. And thus, the force in the x, y, and z direction becomes Fx, F sub y, and F sub z. Okay, in order to apply this equation, we have to break the forces and accelerations into components. The alternative is technically possible but gets a bit cumbersome. That is, you could in principle stay with the vector force and the vector acceleration. It wouldn't add anything new except notational complexity, but we're going to advance by breaking the force into its x, y, and the z components. Z, of course, is perpendicular to the surface of your viewer. In the z direction, there are no forces and no acceleration, so we don't bother to talk about it anymore. So we now need to break the forces into components. For N, and for the spring force, that's very easy because they point along one of the component axes. They have one component that is non-zero. For N, the non-zero component is in the y direction. For the spring force, the non-zero component is in the x direction. What about gravity? Let's advance to breaking the gravitational force into components. So here we are going to break the force into components. When you are breaking a force into components, the force itself is here it is, mg, is always the hypotenuse of a right triangle, and the two components are always the two legs, the two shorter sides of a right triangle. In this case, we have a y-axis, we have an x-axis, so we're going to break mg into its x, what is in fact its x component, and its y component. So in order to do this, we realize gravity is perpendicular. There's a horizontal here. The included angle between the horizontal and the surface of the ramp is theta, and that lets us, with a little calculational effort in plane geometry, get inside the right triangle that's being used to break mg into components. So if theta is the internal angle that we have been given in the problem, and this axis and the ramp are perpendicular because the first axis is the normal to the ramp and the second axis is parallel to the ramp. They're perpendicular, so the triangle down here is a right triangle, and therefore the included angle here is theta. Having said that the included angle there is theta, we notice that gravity is perpendicular to the surface of the table because gravity is vertical and the table is horizontal, and therefore between the vertical and the horizontal there is a right angle. The indicated angle, the double lines, is the complement to theta, and therefore the angle here, the lower angle, internal angle on the component triangle must be theta. Let's remember a little trigonometry. If the hypotenuse is theta, the opposite leg of the triangle is mg sine theta, and the adjacent leg, the leg adjacent to the angle theta, is mg cosine theta. I have indicated both of those components with no sign. They don't have a sign yet. Yes, the vertical force we would say is minus mg vertical direction. However, the sign plus or minus of the two components is determined by which way our component axes are pointing. As it happens, the x-axis is uphill and the normal axis is uphill, and therefore the two components are pointing in the minus x direction and the minus y direction. We'll see those minus signs when we advance to solve. For the forces along the x-axis, we have the spring force. If the spring is stretched, so its stretched length L sub s is larger than L, then L sub L minus L is positive. The spring force points uphill, so the overall spring force is in the plus k plus I hat direction, and therefore here we have a plus sign. Gravity is pointing downhill in the minus x direction, and therefore that's a minus sign, and these two terms combine to give us the total force in the x direction. The total force in the x direction is equal to mass times the acceleration in the x direction. However, here we have specified g. The acceleration in the x direction is 0 because the mass stays stationary. And therefore, the acceleration is 0, and we can solve this equation and get k times ls minus L is equal to mg sine theta. We took the mg sine theta, it was minus mg sine theta up here, and took it to the other side of the equation where it becomes plus mg sine theta. If we divide through by k, we get a result for how much the spring has stretched. And there is our solution.